Okay, in this video I'm going to just give you a couple of examples of setting up a model. We won't actually solve the equations, but we're going to set up some models for a differential equation. And we'll, of course, talk about solving them later, but for now we're just getting this idea of setting up a model and use this three-step process that I talked about in the first video. So remember, the three-step process is coming up with assumptions and then assigning variables basically, and then step 3 is writing the equation. So that's what we're going to do today. So this first one is it's called the unlimited population growth. So this is the idea of you're thinking about people or mold or rabbits or anything that is relatively small population in a large area, where basically the population is just going to grow. So so here we go. Step one is assumptions. So my assumption in this case, let's say we'll talk about, well, just any population growth, but my assumption is the rate of growth of a population is proportional to the size of the population. Okay, so this is just kind of a common sense idea that I think, well, it seems like if a population is growing, that that it's going to grow faster when the population is bigger. So that's just, again, it's just kind of a general thought. This makes sense to me. So I'm going to try to build a model based on that assumption. Okay, so that was step 1. Step 2 is we're going to assign our variables. So my independent variable, we'll call it independent IV, is time. We'll say T for time. And my dependent variable is population. We'll say capital P for population. And so there's my two variables. I just have one independent variable, one dependent variable. So we just saying as time goes on, we believe that the growth of the population is going to be proportional. So when we say proportional, that implies some kind of a growth constant or proportionality constant. So in this case, we're going to bring in, say, a k. K will be my proportional, proportion, I forgot how to spell proportionality. Proportionality constant. We don't know what it is, we just believe that there is one. So it's the thing that links my population to its growth rate. So now, step 3, I think we're ready to write an equation. So keep in mind that we're writing an equation, a differential equation, which means we want a derivative in it. So if we believe the growth rate, and when I say growth rate, that makes me think of a derivative, right? So the growth rate could be represented by dp dt. And there I'm using Leibniz form or notation. I think it's really my favorite because it reminds us that this is a derivative, but not only it reminds us what is changing. The population is changing as time is changing. So I'm going to generally use Leibniz notation in this class. Of course, you could write this as p prime, and there's a lot of different ways to write it. But so anyway, we're going to say that the growth rate of the population is equal to some constant times the population itself. So as the population gets bigger, we're going to multiply it by some number, and that'll mean the growth rate will get bigger. Okay, so that's the basic idea. And so then the next step, of course, would be to try to solve this equation, this differential equation, which means we're going to try to come up with a p, whoops, the daisy, come up with a p of t that would make this equation true. So in other words, if I need to come up with an equation that when I take the derivative of it, it will look something like this. Okay? Now, just to give you an example, this is kind of a trivial example, but if we let P of t equal 0, meaning that we have a population, say a town with nobody in it, the population is 0, this equation, the constant function of P of t equals 0, would make this equation true, wouldn't it? Because dp dt, the derivative of 0, is 0, and of course k times 0 also is 0. So this is the equation, this is a function that would make this equation true. So that's a possible solution to this differential equation. Now there are other solutions, and we will get to finding them. But this is a special solution. It's called the equilibrium solution. And often when we talk about differential equations, it's sometimes useful to find the equilibrium solution. The equilibrium solution is the solution that's that doesn't change. Okay, so a couple things about this differential equation we have right here is this is a first order differential equation, and it's also an ordinary differential equation. Okay, it's first order equation because it does not have any second, third, or fourth derivatives, and it's called an ordinary differential equation because there's no partial derivatives, which if you haven't taken Calc 4, you may not know what a partial derivative is. So, but you could tell this is just a normal derivative. Okay, so let me do another example, a little bit more complicated. So let's say that this model doesn't really take care of our situation, and as we study it further, we come up with some further assumptions. So I'm going to adjust my original assumption. I'm going to say when the population is small, for a small population, the growth rate is proportional to the population. So that's the same assumption we had earlier, and we're also assuming that it's increasing. Proportional, it's a direct proportion, so it's increasing. The second assumption I'm going to make is for a large population, and what I mean by a large population is close to carrying capacity. So the idea in populations, whether it be a carrying capacity, whether it be a rabbit population beginning to fill out the meadow, or a amoeba population filling out the petri dish, or as a population gets closer and closer to the what we call the carrying capacity, the amount of the size of population that the place you're living in can handle, the assumption we're going to make is that the population will decrease. So this is kind of a little bit more complicated, which means probably it's going to be more realistic. So when the population is small, the growth rate is proportional to population increasing. So as population gets bigger and bigger and bigger, the growth rate will get faster and faster and faster. But then as the population gets too big, in other words, close to carrying capacity, then the population will begin to decrease. Okay, so that's my two assumptions. So now we go to step 2. We still have t equals time, and we still have p equals population, and we still have that k, which is we'll call it, since we know kind of what it is now, the growth rate coefficient. coefficient for small populations, that is. And then we have a new variable called n, we'll call n for carrying capacity, which is that kind of the size of the population that whatever area we're talking about can handle. So now we're going to come up with an equation that that binds all these together possibly in some form or another. Okay, so that was my step 2 that I just did. So this is a parameter, the carrying capacity, because the carrying capacity for this, for a particular model, is not going to change. There'd be some population that that area can handle, but it would change from model to model, of course. Or we might take a guess at what the carrying capacity is and find out that it throws our model way off. So then we might come back and say, well, maybe we were wrong about the carrying capacity. It actually could hold more or hold less. So it can change, but it's not changing with time. But what is changing with time is the population. So these two, the k and n, are parameters, whereas t is the independent variable and p is the dependent variable. Okay, so the idea is that this is going to be similar to the last one we just did. So the change in population, so the derivative of population, is still going to be equal to some constant times p, but we need something else in here to make to take care of that second assumption. Okay. So let's make sure we're clear on these assumptions. Basically, what this is saying is that when, I guess we could simplify it to say when p of t is less than n, the derivative of p is greater than, and this is basically saying when p of, or dp dt is greater than n, then we would say, no, I'm sorry, when the population is greater than n, p of t is greater than n, then dp dt would be less than 0 because it'd be decreasing. So that's kind of what we're trying to go for, and we're trying to indicate that here. So if I just multiply k times p, then that would satisfy the first assumption, right? But then I need something in here to make it so that as the p gets closer and closer to n, we need that to switch. And so one way to do that is we can take this and leave k as k, and we're going to put in here 1 minus p over n times p. So notice if I just multiply to get a better look at this, we got dp dt is equal to, so this would be, we're multiplying k times 1 times p, so that would just be kp minus k times p squared over n, right? So notice what happens here is this is just going to, actually I don't know why I divided that up, we don't really want to do that. What's happening here is that when p is really close to n, this is, I'm sorry, when p is a lot bigger than n, this is really large and this is going to be negative. When p is really small, so not even close to n, this will be really small and it'll essentially just be k times 1 times p. So as p gets closer and closer to n, this is bigger, so we're going to take less and less from 1, so the population is going to slow down. So you can see that the population would start off growing really fast. As p gets closer and closer to n, it's going to cause that growth rate to get smaller, and so it'll start to taper off. And of course, once p gets bigger than n, then we're taking something bigger than 1 away from 1, so this would be a negative number, which means that it's going to start going down because we'll have a negative rate of change over there. Okay, so that's the idea. And this, of course, is also a first order differential equation because there isn't a second derivative, third derivative, etc. We also would classify this as nonlinear because of that p over n in there. We got some, it's not just a simple linear equation. So anyway, there's a couple examples of walking through the 3 steps of coming up with a model. So in our next video, we'll start talking about how we solve these things.